Okay, the next subject we're going to be covering is looking at fasteners in mechanical design. Okay, and these are important because as you start putting assemblies together, which is going to be kind of the next thing we start looking at here in class, is making what we call a full set of working drawings, where we've got now, intentional parts that are going to go together to make an assembly, make something work. Okay, so when we do that, inevitably we've got to make those things fit together and fasten so they don't fall apart. So we're going to have to use some common fasteners. And so this presentation is going to be showing us a number of different types of fasteners that we'll consider or come upon as we design. So the first one that we have here, this is called a hex head cap screw. Additionally, unfortunately, if you're not in class, you won't get the full experience, but I'll be passing around some parts and things to, kind of have a show and tell, if you would, for some of these items as well. But the PowerPoint does a nice job of the illustrations as well. So this is called a hex head cap screw. And the hex head is obviously called a hex head because of the shape of the head that it has. And then we're going to need, for instance, like a wrench to tighten and loosen that up. Notice that the body is a threaded item, meaning that it has these spirals going around. Now, we're going to be talking about these spirals and how to call them out on a drawing, and there's a standard associated with them as we kind of work through here. But this is what we would consider a threaded fastener. Okay, so those are the threads, as we call them. And I'm sure you kind of have heard those things along the way. The next type here, the socket head cap screw, is probably the most popular type of a fastener that we use in mechanical design. And the reason being, although you don't see it here, there's an indent here with a hex. Now, underneath our camera, I do have a couple of socket head cap screws here. And I hope you can kind of see it. I don't know if you really can, but you would need an Allen wrench or a hex head type of a wrench that is going to actually be able to go in there and loosen and tighten that up. Okay. Now this is important. This is important because when we're dealing with especially parts that are guarded and we need to protect people from whatever the machine may do if it injures somebody, we have to use fasteners that are going to require what we call official tools. Okay. So on it's coming up on the third slide away from where we're at, I'm just going to use this as an example. This has a flat head on it. Okay. So what we would use is a flat, head screwdriver to tighten or loosen it up. But you can also use a butter knife. You could also use a coin, like a quarter or a dime, and people have been known to loosen things up. Now, by OSHA standards, especially when we're dealing with guarding and safety, we have to use fasteners that require an official tool like an Allen wrench. Because, and now this is how it was told to me, I'm not saying that this is, exactly the rationale, but for instance, if somebody can just pull something out of their pocket and loosen up a guard to get at something, evidently the company is at fault because they're not using a tool that can actually loosen that up. But if they would have to actually go and get an Allen wrench from a toolbox and have to loosen it up, now all of a sudden the company has put in place every possible thing to stop that from occurring. I don't know, but it's an OSHA standard. So you're going to notice that in mechanical design, we do not use slotted anything because most often we're designing for industrial purposes. Now, if you go home and you look at your dishwasher or your washer, there's going to be a lot of slotted heads things here because that allows, kind of the consumer to maybe do some troubleshooting or whatever. So, and it's not as, safety oriented. So just know that socket head cap screws are going to be what I am going to be expecting that you're going to be using on all designs. If I see any slotted head, anything, we can't do it. They are going to be in the toolboxes of the CAD programs that we have. Okay. But they're not appropriate for the industry that we're training you for. Okay. So socket head cap screws. Okay. We're going to notice too, we're going to see these abbreviated as SHCS. And for obvious reasons, but it's also when we fill out what we call our bill of material for assemblies later on, we are going to be using that abbreviation, okay? Because then it's not as long in the title, in the bill of material. The next type that we have is a flat head cap screw. Now I have it in the slotted form just because this is what people gave me. Okay. So you'll notice that this is tapered here. So underneath my camera, I'll make this actually bigger. Underneath my camera, you'll see the side of it. It's an intentional taper and then the threads start. Now, like I said, this is a slotted head, but the intention of this would be to sit into a recessed groove called a countersink. Okay. And it's going to sit down in there nice and flat. Okay. So you would actually have to design, if you specify this type of a fastener, then you have to design for a countersink at the appropriate size for that to fit into. Okay. And then that's always going to be flush with the surface. All right. The next one is a button head. I think I have a button head in here. I do. A button head is exactly that. It has a rounded top to it. And then the threads start. So under here, this is a button head. I'm sure you've seen these before. They're usually used when we put it in, you know, here, it makes a lower profile on the top of the part. Okay. As opposed to, I think I have a socket head cap screw here. A socket head cap screw would be sticking out of the top. So you can kind of see the difference between those two. Okay, still provides the same type of fastening, but a lower profile. Now, if you wanted the socketed cap screw to be down below the surface, we would add a counter bore. Okay, and we've done that on some of the drawings we've seen already, but this would be actually how it would look, you know, fitting inside of that counter bore. But if you don't want to add the extra operation and a button head can, you know, suffice, then that's a way to accommodate that and be lower profile. So button head cap screw. The next one is a pan head machine screw. This one has a slot, so we probably won't be seeing these or even considering these, but this is another type of fastener you may see. Here's a flat machine screw. So again, this is going to have the taper on the top, but it has a slot on it. The next one is a set screw. A set screw is basically a threaded body without any sort of a head. Okay, and I've got two examples here. So the point here is going to be, there's different types of points that are available. And in the handout that we have, we'll see some of them. You'll notice that this one has kind of these like, little like edges on them or teeth. And so it's actually designed to actually like kind of get into and grip into a surface when it's tightened so that it doesn't move. Others are just going to be flat, like the ones that I have here. These are just flat. So, so I'm going to go underneath here. So it's just a headless fastener, but then you'll notice that on the ones that I have, these have those hexes in them, like the sockets that you need to, again, use tools to tighten them down or loosen them up. So these are just set screws. Okay. And I'll send my little box around once we kind of get through everything so that you guys can look at them. The next one is a shoulder bolt. Okay. I don't have a shoulder bolt in my box here, but the shoulder bolt is going to have a similar cap screw head with a hex in it. But then you're going to notice that this is the shoulder part, and this is going to be ground to a very precise diameter. Okay. Most often this is going to be used to maybe mount a pulley on it or something like that. Okay. So there's an intention there. And then after that is going to be the threaded portion. So usually here you're designing another element to actually be on there. The next one is going to be a number of different types of hex nuts. So we've got a finished hex nut. And then we've got heavy hex nut. This is going to be on situations where we have bolts going through something. And then, and maybe multiple parts. And then we're going to put a nut on the backside to hold them together. Okay. So it provides kind of the friction, if you would, that it's going to be together. So here is a jam nut, a flange nut has the extra flange on here, kind of like a built-in washer, if you would. And really the purpose of that is to distribute the load over a larger surface area. The next one we have here is a nylon insert lock nut. And this insert is going to serve the purpose where if we end up having high vibrational areas where we tighten it down, what can happen over time, because there isn't, those threads aren't perfectly fit to whatever they're threading onto. What can happen is they can vibrate or loosen up over time. So this nylon insert can help to actually minimize that from happening. And then here's a washer, just a standard washer. Here's a split washer. This also is going to aid in the split washer. And so like this surface is higher than this one. And when we actually tighten this down, this creates a little bit of resistance or springiness. So it's going to then minimize that opportunity for what would probably be a nut on the backside from loosening up. Very similar, different design. Here's a lock washer with external teeth and then internal teeth. And again, if we would look at the side of these, it's kind of like a crown. So when we tighten down, it's going to create that little bit of springy pressure that is then going to minimize the vibration or rattling off. Another type of fastener that we see, and although it's not considered something that's going to tighten something down, it's usually used for alignment. This is a dowel pin. Okay, so if we have a critical feature where we need to align a cover, okay, we'll have dowel pins there, and then we'll usually tighten down with, headed fasteners after that. But this is going to be used for positioning something accurately. The next one is a spring pin. Notice that there's a, there's a cut down the middle here. And what we do is this intentionally is kind of like open, but now when we press it into a hole, it's going to have that ability to collapse down and then stay in place. Okay. So it's kind of like a force fit, if you would, into a hole. The next one is a cotter pin. A cotter pin is going to be used to keep rotating elements on a shaft. We see them a lot in agriculture and maybe even lawn and garden instances where we have, your wheels on your garden tractor. On the outside, you're going to see these cotter pins on there. So the cotter pins go through and then we split that side or the two ends so that it then bends over and stays in place. Once a cotter pin comes off, it's kind of done. You have to replace it because it's bent, but it's by design to stay in place. The next one here is a woodruff key. A woodruff key is going to be an element that will allow for parts that are rotating to be relative to one another. For instance, if we want to put a gear or a sheave on a shaft that's rotating, the inside of the shaft bore needs a way to kind of grab onto the element so that they rotate at the same speed. So a key is like part into the shaft, part up into the gear, for instance, and now when it rotates, it's going to bring it along with it. Okay. So keys are used a lot for transmitting torque, transmitting rotational speed. They can be in that woodruff form or they can be in square forms. And then we've got retaining rings. Retaining rings also kind of act as a shoulder. Okay, so we're going to put this retaining ring where we don't want something, if you would, that's rotating to walk off the shaft. Okay, we would create a groove for this, and then it would be, upwards of the groove. And then we could do the same thing internally for internal features. Okay. And then kind of getting back to thread designation. So the next thing that we're going to be looking at is a handout, which goes into, I call it the weeds of all the details that have to do with thread designations. But here's just a little bit of an insight. So you'll notice here that I have a 1/4 20 UNC, 1/4 28 UNF. So this is looking at a 1/4 inch diameter bolt or a screw. And the dash number after is called the threads per inch. So this means that in 1 inch increment, I could count 20 threads on this designation. Okay. The next one, it would be what we call a fine thread, meaning that in this case, I have a 1/4 28. And now within that same inch increment, I can count 28 threads, meaning that they're closer together. It's a finer, what we call pitch thread. Okay. And we'll look more at a number of different designations here, but that's just kind of an overview of the types of fasteners that we're going to see. Now, in terms of fasteners, you're not going to have the responsibility necessarily of drawing the fasteners, okay? But you will be using them in your design to keep things together. And your company probably won't even be making any of these fasteners. We buy these. These are going to be elements that, as you know, you can go to the hardware store and there's buckets of them, right? And you just pick out the kind that you want. Similar thing at your companies. They're going to be buying in bulk fasteners like washers and nuts, and especially, these socket head cap screws are going to be in all different sizes, different diameters, different lengths, all that kind of thing. And then you're going to incorporate them into your design. Okay. So There's only a couple here. I'm going to keep them just a little bit longer. So now what we're going to do is kind of getting that overview of the fasteners. Let's then look at the other handout that I have in that module. Okay, actually in the assignment, I think. Yeah, the module, the assignment, sorry. So if we go to, oopsie, cancel, I want to save this first. If we go to our module 6, and down to our assignment for fasteners, okay? I have a handout in here and a stare-it drill chart. So let's look here. Even though I'm not going to talk formally about the assignment, you're going to use this handout for your assignment. And I'll get to that in just a bit. So let's look first at the fastener handout. This is the PDF. And when we pull it up, it's like 34 pages long. So I did not make copies of this for people in the room even. So we're going to reference this online. And this is just a little bit of a table of contents of what's coming. But I want to kind of walk through this so you can see the information that's here. Now I'm going to go over it in a high level, and the assignment that you have is going to have you pull out of mostly this handout, the information to fill in. Okay. So first it's kind of starting out here and giving you some, some symbols and things that you might see as you go along, but it talks about threads here. Okay. Threads. And really it's identifying that we have internal threads, we have external threads. Internal threads, go back underneath here, are going to be, and I hope you can see this, there are 4 internal threads here. So 4 threaded holes, we would say, on my part. Okay. External threads are going to be anything that are on the outside of a part. So a threaded fastener, these are external threads. We can also add threads to, for instance, like the end of a shaft. Okay. Those would be external threads. So this is external. This is internal. Okay. There's 2 different ways we make these. We make the external, well, there's a couple different ways we can make external threads. Sometimes they're forged in place or cold rolled. Other times they might be created and cut on a lathe, for instance. Okay. And then when we do it internally, we need to actually use a special tool called a tap. And we'll see that in a little bit. So internal, external threads. Okay. Now, as we look at the thread form, and this is there's a lot of different thread forms for different purposes, but we are going to be just focusing on threads that we're going to be using for fastening in mechanical design. Okay. So this is a thread profile. And you'll notice that if you look really close at threads, and I'll start handing some of these around. Okay. I don't want to give them all up. I'll start handing some of these around. Give you this one, this one. And I'm going to keep some of the other ones, and then I'll give you, I'll do the rest after we're done with our lecture. So I'm going to start these. I'll start on my video. So this profile is important to us, okay? Because as we look here, these are kind of, some of the things that we're going to be talking about threads. So first and foremost, the pitch of the thread is going to be the distance from one point on one thread to the very same point on the next thread. Okay. Now the side of if you would, the tooth here is going to be that part. And then the root is at the very bottom. Additionally, at the very top, this is called the major diameter. So the minor diameter is at the root. The major diameter is over what I call the top of those threads, okay, or the crest of those threads. Additionally, there's going to be a thread angle. Now, the type of thread that you have on an external thread has to be the same type of thread on an internal thread for them to actually fit together, okay? Additionally, they have to have the same pitch. They have to be the same distance apart. You can't have coarse threads and fine threads intermixing one another. They're not going to thread together. Zoom out just a little bit. So as I said, there are 2 main series, but there is a third that we don't use very often. There's coarse, meaning that the threads are the furthest apart for that standard. There's fine, they're going to be closer together for that standard. And then there's extra fine, where they're even closer together. in mechanical design, we are going to be using coarse threads and we're going to be using fine threads. The extra fine, we really never see. Okay. That's going to be for industries like watchmaking or, you know, very, very small, maybe clocks, that kind of thing are going to have the extra fine. Okay. Now, when we talk threads per inch, this is exactly what it sounds like. We have, you know what? I have a problem. I have this jacket on. Side story. So my daughter got a new Apple Watch. Okay. So she's like, Mom, do you want mine? I'm like, well, yeah. Okay. I'll take it because I bought it originally. That's fine. So I'm like, okay, cool. I'm going to have an Apple Watch. This has been the biggest pain in my butt for like the last 3 days. It's no, it's not even about that. It is so distracting. So yesterday, what I did was it went off in one of my classes. So I put it in the pocket of my sweatshirt at my desk and I forgot that it was in here. So now it just went off. Now the settings on it told me, and I don't claim to be a techie person, but I'm not like illiterate either. So I'm following along and it says, you want your settings to match whatever your iPhone does. So I have my iPhone on silenced or maybe vibrate, right? Well, how come my stupid thing is ringing? Why is this ringing? So that's why it went in my pocket. Well, now that it was kind of chilly in here today, I put my sweatshirt on. Nobody wants to hear this, but that's why it went off. It's not because I'm like being ignorant. It's because this stupid thing is probably going to be on Marketplace very soon. Hate it. Just a regular watch with a face. That's all I need. I don't need to know how many steps I have in a day and feel bad about myself when I go to bed.
The time. Yeah, I like those.
I know, just the time. That's all I need. That's all I need. Okay. Anyway, so sorry about that. I apologize. Ugh. Okay. So threads per inch are exactly that. We're going to measure literally an inch and we're going to count how many threads are within there. Now you don't have to do that, because the designation is that. So when we have, for instance, that 1/4 the diameter on the outside of the threads is going to be my 1/4 of an inch. And then when I measure an inch, I'm going to count 20 threads. That's the spacing. Now, it doesn't mean that the fastener has to be even an inch long. It can be shorter, but if I would have an inch of threads, there'll be 20 in there. Okay. If it's the fine designation, I would have 28 in there. That means that they're closer together within that very same inch. Okay. So that's what the threads per inch mean within the series. So coarse, fine, and extra fine, as we said earlier. Now, additionally, there's class of fit. So a class 1 fit is the loose fit, meaning when I thread these together, I can actually feel a little bit of a difference. Okay. But class 2 is like the standard. So it's kind of like boilerplate. Like if you're expecting, to get a fastener, and it's probably a class 2. Only if it's a class 1 or a class 3 do we specify it on a drawing. If we don't have any class specified on a thread designation, it defaults to class 2, okay, which is like the standard. Class 3 is then going to be a tighter fit. So when we thread these together, we're not going to feel much slop in there at all, if any. Now, additional to the designation, there you could see a 2A or a 2B. A 2A means that it's an internal, and a 2B, 2A is the external, it's right here. A is external, B is internal. Okay. And again, we usually don't see those on designations because I can tell this is external and I can tell that's internal. Okay. So you don't need to add the A and the B usually. So, but you may see it and you might wonder, what is that A and B? It's just calling out if it's an external or an internal. Okay. So on this next page, I'm gonna zoom in here. We're gonna look at this designation. This is the full deal. So we always start out our thread designation with the nominal size. So in this case, it's 0.25. You saw earlier on that other slide, the 1/4 inch, like fractional increment. It can be either way. The preferred way is the decimal, but you'll see it both ways, or people are gonna say 1/4 inch. So a lot of times you might see the 1/4, totally fine. So that's going to be your nominal size. Now, the nominal size is always, always, always going to designate the size of the diameter over the major diameter or over the crest of the threads. So when I measure this with a micrometers or a calipers, if it's a 1/4 inch fastener, it's going to be a 1/4 inch right here. That's actually also the maximum size. We call that the maximum material condition because this is an external feature that's as high as this can get. So your nominal size and your maximum size are always the nominal, always. So if it's a 1/4 20 socket head cap screw, that's as big as that's getting. And it's going to be the diameter I'm going to see over the top here. Okay. Now, after that, there's going to be a dash. Okay. And after the dash is going to be the number of threads per inch. So in this case, it says 20. Then immediately after the 20, we're going to see UNC, which is the coarse thread designation for a 1/4 inch. If this was a fine thread, it would be a 1/4-28 UNF. We always add those. You might say, well, if you have the 20, why do you need the UNC? You just do. Okay. You always call it out. Now, this is where you can stop the designation. You can stop right here and everybody's going to know what you need. Because after that, I can look at my thread and I can see is it internal or external. And the assumption is it's a class 2. Done. Okay. And then after this, there might be special notes that might be added. The only time you're going to see, if we look down here, let's see. The only time you're going to see a left-handed is when it needs to be left-handed. By default, our threads are always right-handed, meaning we tighten them righty-tighty, we loosen them lefty-loosey. If you need to tighten something on a left-handed thread, and this sometimes occurs when we have rotating items, because if it's rotating in a certain direction, we don't necessarily want it to or to loosen up, I should say, that's a better word. Okay. So we might put those threads in the opposite direction. Okay. So you'll only see a left-handed thread if it's a special designation. Otherwise, like I said, we would normally stop the designation right after the UNC or the UNF. We're done. Okay. Because 2A is assumed or 2B would be assumed. Okay. And then only the left hand would be added. Okay. Now metrics. Metric thread designations are a little bit different, but there are some commonalities here. So first and foremost, you're going to notice that we put an M in front. An M and an MJ are just two different thread forms. Okay. M is going to be the most popular that you see, and it really looks just like the ones that we have for English. So we're going to have an M in front of the nominal size again. So just like the 1/4 inch would have been a diameter over our crest or over our teeth, the M8 is going to be that nominal value. So if we go underneath here, it's going to be 8 millimeters is going to be the diameter of, the major diameter of those threads. Okay. Now you'll notice that we have a by instead of a dash, and the by, the number after the by is the pitch. Now the difference here is that instead of measuring a length and counting the number of threads, what they do is they say the distance. It gives you the pitch. So if we go back up to the beginning of this section right here, they're giving us the distance from the one point on a tooth to the next point. Okay. So on that M8, was that a by 1.25? This would be 1.25 millimeters between each one of the threads. Does that make sense to everybody? So they call it out just a little bit differently, just a little bit differently. Yeah. Now, after, you're going to notice the designation. This is if there's a clearance hole that you're calling out, and this is going to be the tolerance that you're calling out. So that's what the H or the 4H for 6H. Normally you will just see again the M8 by 1.25, and then we can see, is that an external? Is it an internal? And then it's done. And then we would add a left hand if we need it. So the additional information in there is kind of like optional. It is optional. It is optional. The M series. Okay. Thread designation. So again, we would stop after the number after the by. Left-handed threads. Okay. And now we have encountered some of these symbols as well. And we can see them on my block here too, like in person. So we've already talked about counter bore, spot face, counter sink, diameter symbol. We haven't encountered the square symbol, but this would be if we had a square shape that we were trying to achieve. And then we also have seen the depth symbol to call out the different designations. Now, as we know, the counter bore is going to be something that is going to accommodate the head of like a socket head cap screw, which we saw in my block here. A counter sink is going to be for one of those flat head types of fasteners. And then a spot face is just going to be a depth of a counter bore. So it's really the same symbol as a counter bore, except it only goes a little bit to clean up the surface. It's not going to bury the full size of the head. And then we've used these symbols before, so I'm not gonna you know, really go over those. I do like this illustration right here, figure number 9, where you can see the differences between the counter bore, a counter sink, and a spot face. Okay. And you as the designer, these are the things that you're drawing and specifying. Okay. So those are important. Also just noting, I know we've talked about this before, but if we have a hole that's going to be to a blind depth, the blind depth just means that we are going not all the way through, but we're going to be going like a certain depth down. So we know how to call that out in back of it, but when we specify it, remember that depth is going to be to the flat of the drill, not to the point. Okay. So the point is going to go further beyond. Okay. Diameter symbol. And then here is where we have our chart where it starts with the standard thread designations. So on the left-hand column here, you're going to notice that we have nominal diameter. Okay. Now we always start, the smaller sizes are in, if you would, number form, but then starting at 1/4 of an inch is when we get into kind of those fractional sizes. Okay. The couple that are popular, if you would, that you may encounter are going to be the number 8, the number 10. So this would have like the number symbol in front of them. So it would be a number 10, number 8, and then starting with the 1/4. Okay. Now that's going to be your nominal size. So if you know the size of fastener that you want, so a 1/4 inch fastener, then if I go back to the top here, you're going to notice that we have a coarse or UNC designation. So Unified National Coarse Thread. So the standard in that category then is for a 1/4 inch fastener to have 20 threads per inch. That's a UNC. So it would be a 1/4-20 UNC would be the call out. Okay. Now the drill, the tap drill here, this is going to go along with the size of the the coarse or the fine threads. So for the 1/4 inch, this drill size is a number 7. So. Now, I don't know if these actually go together for sure, but I'm going to go underneath here. When we create the threads, okay, so on those threaded holes there, before we're going to actually what we call tap the threads in or create the spiral on the inside, we have to drill out. Okay, so we're going to put a drill in there. This isn't the drill size, but we would drill in first and get most of the material out. This drill size corresponds to the root diameter of the thread that I want to accommodate. So I'm going to take out most of the material. Okay, then what I'm going to do is I'm going to go in with, this is a tap. Okay, so notice that there's the points on here, and those are going to correspond to the size of the thread that I want. Then this is going to go in and it's going to rotate. Okay. And it's going to create the threads. Okay. So it's like creating the spiral, if you would, going down in there. All right. And that's what the tap does. The tap cannot remove all of that internal material. So whenever we tap holes, whenever we make threaded holes, it's a 2-part process. We need the tap drill corresponding to the tap size. So these two are a match set depending on call out. So that's what we see here. So if I want to create a 1/4-20 internal thread, I need to start with a tap drill size before I actually tap. And that tap drill size needs to be, to accomplish the 1/4-20 specification, a number 7 drill. Okay. Now what's a number 7 drill? All right. We have another resource. If we go back to, I can do this on here. If I go back to my assignment on fasteners, you're going to notice that there's a Starrett drill chart here for you. Okay. You may have seen these in the machine shop or around. Okay, does this look familiar? These are little cards that have, it's front and back here, okay? But what we have is, we have our tap drill, and it's gonna give us the actual decimal equivalent size, okay? So this is, I want a number 7, right? So I wanna find a number 7 drill, tap drill size, number 7. Well, of course, we're not gonna find it because that's the one I want. I don't know if I see it here. Tap. That's, oh, sorry, that's the tap size, my tap drill size. Drill size. Should be right around the quarter inch. Do you see it? Where do you see it? You've got 3/16. Oh, there it is. There's my number 7. Thank you. So number 7 drill corresponds to, I'm not gonna be able to select that, a 0.201. Now remember, my outside for a quarter inch is 0.25. So I'm gonna drill first with 0.201. I'm gonna get all that material out, and then the tap is gonna create the major diameter and the spiral in there so that it's going to then fit with a quarter inch. So again, a tap can't take it all out in one operation. I have to drill first, number 7 in this case, and then I'm going to create my threads after that. Okay. I think. Back here. All right. So moving along here. Threads. Okay. And so then what you'll notice is as we move along to the right on this chart, now we've got the fine threads. So we can go to that same line, a quarter inch. If I want fine threads, there's going to be 28 threads per inch. And now I need a different drill size for that to make it. And then lastly, I have the extra fine. And so you'll notice here I can get 32 and then the corresponding drill size, or I'm sorry, yeah, 32 and then the corresponding drill size here on the same line. Okay. So you'll notice that there are different coarse and fine threads for each one of the different sizes here. So for a 1/2 inch nominal size, 13 would be my coarse thread designation. So it would be a 1/2-13 UNC. Or if I wanted the fine threads, it would be a 1/2-20 UNF. Okay. Zoom right here. So this is another picture of that process. So here's the drill, here's the tap. And then if we wanted to actually assemble something, we would put our fastener through and, you know, it looks like a cover or a plate of some sort. Now, when we call it out in a drawing, okay, this is how we're going to draw it. So this is called a simplified version of the thread. So you'll notice that we have to draw it with 2 holes. The first hole on the inside here, okay, is going to be the nominal size. And then we add just an outside hole, and it's going to be a dashed line or a hidden line around the outside. Now, why do you think that we have that dashed line around the outside? Yes, it's perfectly said. It's the hidden space where the threads go. So if I look inside or underneath here on my threaded holes here, I see the very inside, but then when I tip it, I've got those threads that are actually jutting into the material. Okay. Now you don't have to make those to the perfect size. What we want to see is that there's an offset to represent a threaded hole. So normally in an inch increments, a 32nd larger on the diameter, just doing an offset of a 32nd of an inch in AutoCAD, and then changing that line style to hidden is all you need to do. But you have to show it with two holes. So, or I should say 2 circles. So the internal circle is going to be visible. The outside circle is going to be hidden. And then your call out is going to call out that designation. So in this case, this is a 5/16, I think, -18 UNC. Now, adding the 2B again is kind of redundant. The 2 means that it's a standard fit, which is going to be assumed, and the B says it's an internal feature. I can see that. Okay. So if you stop it right after the -18 UNC, you're totally good. You have enough information to create that. Okay. So that's how we show all threaded holes. Any questions on that? So we already talked about different types of fasteners and heads. So I'm gonna gloss over this. Now, this is a typical way that we are going to assemble parts. So when we want to fasten something together, for instance, putting a cover on something, what that means is we're going to have our fastener. It's going to come through. And if the cover is on the top here, we're going to provide what we call clearance holes in that cover. So notice that there's a gap, right? And so that way the fastener can go through, but then in the piece where we're adding the cover to it, notice that now we have threaded holes. This is called a fixed fastener type of an assembly, where we have the clearance on just one part and we thread into the other. The other way that we can fasten is down here below, where we have clearance holes going through both parts. And then we can put the threaded fastener all the way through. And then we put, on the back side, maybe some washers and a nut to hold it in place. This is called a floating fastener situation, okay? Now, when we thread here, the number of threads or the amount is down here in the reading. So I'm going to let you find that because I believe that's one of the questions. So you can't just put a fastener in place and have 2 threads and say, oh, I'm threaded in, okay? You have to have a minimum amount, and it's based on the diameter of the actual fastener itself. So I'm going to let you find that. That's one of the questions, and I'm intentionally not going over that because I want to make sure you read this, okay? So there is a minimum number of threads based on the size that you have to go down, and you'll find that in the reading. And then it talks about set screws, which we already saw some examples of. This is where we see some set screws on collars that are going to go through so that the collar doesn't spin around. And all the different types of like ends that it has depending on the application. Okay. And then there's the appendix. The appendix is going to just give you more information on standard sizes for the different types of fasteners that are here. So socket head cap screws and all that kind of stuff. So these are nice charts if you would want to draw them or know what the relative size was. What I will do, just want to get through over here. Head dimensions. Okay, and at the very end, you'll notice that we have a chart that is going to have bolt markings. Okay, you may or may not know this, but the markings on bolts are going to equate to the grade or the class that they're in. Okay, and then that is going to then equate further into how strong they are. Okay, so there is a little exercise at the very end where I ask you some questions about that. Okay, so I want to look at the assignment that I have for you guys. So I'm going to pass out in class here the assignment, okay? And then we'll look at it together. If you're not on campus, you want to go to the assignment, and it's going to be this Mod 6 assignment, Fasteners PDF. So I'm going to get this passed out in class here. You want to fill it out and then we'll okay. Now there is, let's look at this and kind of see what the assignment looks like. So this is related now to the handout that we just went over. Now, I'm not going to guarantee, this is what I want you to do, just like you would in the real world. So I gave you the resource, the handout that you're going to reference, and it's in that assignment Dropbox, okay? So the handout that we just kind of went through, that PDF, you're going to find most all of the information for this assignment in there. So for instance, you want to, in this first part, you want to fill in any of the blanks in the charts below. So you're going to find what the size is for a number 8 drill. So in that handout, actually not the handout, but you're going to find in that stare it or star it, however you want to say it, drill chart, you're going to find the number 8 drill in here and what that size is. Okay, so this will be a resource. You can do that. The other place that you can look is online. Okay, now I will guard against online for if you use any information, if you Google it, you can. Okay, you can try to use, if you can't find something in the handouts, you can Google it. I'm fine with that. But as you know, when we Google something, I am going to encourage you not to go with the very first resource, meaning it's always good practice to try to find that very same answer in at least one or two other places. Okay, so that you can be like, yeah, this is a good resource, or a verified resource. So if you know you're using, if you're on the Machinery's Handbook, site or something like that. So those need to be filled in. Now, something I did not go over with you guys is standard clearance hole size. Okay. All right. So if you're not listening to me, come back to me right now because I want to let you in on this. So for this one, standard clearance hole size. The standard clearance hole size is going to be a 32nd larger in diameter than the size of that fastener. Okay. Than the size of that fastener. So for instance, if I have a 1/2-inch fastener, it's going to be the standard clearance hole size is going to be 1/32 in diameter larger. Okay, so that would be 17 30-seconds, right? 16 30-seconds is a 1/2 inch. So an extra 32nd of an inch would be 17 30-seconds. Okay. When you get down to number 8, number 10, those two are numbers. You're still a 30-second larger. So you're going to have to figure out what is the number equivalent of a number 8. Now that's not a number 8 drill. It is a number 8 fastener. Okay. It's a number 8 fastener. Different. Okay. So, so you're gonna have to find that and you're gonna go a 30-second larger there. So 0.0325. All right. So that's that. And then as you go through here, I believe everything else is on here. Now, if you notice there's something like, for instance, I say draw a sketch of, you have to be neat and orderly on this. Okay. Yes, it's a sketch, but if you know you're not great at sketching, get out a straight edge. Okay. And use pencil so you can erase. All right. If you do a chicken scratch here, that's called 0 points. I need something neat that I can see. Okay. And then make sure that you're labeling the major, the minor, and the pitch diameters. Okay. Threads per inch, that's that. If there's anything here again, if there's a describe and you don't know what words to use, feel free to draw a picture that is clear and readable. All right. And yeah, there's some true false, there's some, fill in the blanks, that kind of thing. So, so that's the assignment. Now, how to hand this in, what I need you to do is to scan or take pictures and add them to the assignment here, then upload them. All right. So you're going to be printing this out, filling in all the answers manually, if you would, but then uploading this to the assignment. Now, I just want to remind you that when you upload, check what you're uploading, meaning what is the quality? Don't look at it and be like, yeah, it's fine. Make sure it's readable. Make sure it's not blurry. If it is, it's a 0. Okay. I can't grade it. And it's not because I'm being picky about it, but if I can't see it, if I can't make out what's there, I can't give you any points for it. Additionally, on any sketches, if I can't read your writing, if you have to come up to me and say, well, that's a 5, not an S, I'm not taking time. There's 20 people in class. All right. And not that I'm glancing at it. I want to go through in a really fast, but I'm also not going to spend time on yours because you didn't take the time to be a little neat about it. Okay. So, so that's the deal. Any questions? So you should be able to upload photos. The thing about photos, I want to remind you, make sure that you're directly over the top, like you're looking straight down at it. Don't take a picture at an angle like this because I can't see the far away stuff. Okay. It's blurry and it's hard to read. PDF is the best. So if you find, and then there's a ton of them, there's little, like I use Tiny Scanner on mine. What's nice is it takes that picture, it converts it to a PDF. And now it just takes all of that like blurriness or even the different lighting out of it. And it becomes, a nice document to look at. Okay. Any questions at all? So For module 6, these are due at the end of this week. These are two kind of, I'm going to call them two small assignments. There's not a whole lot involved in it. It's kind of going through that material that we went over, making sure that you hit, if you would, the highlights. And then the other thing that you're working on right now is finishing up the module 5 application drawings. Okay. So if you have any questions, for Friday, like we say, you know, normally I'm not going to be going over any new information. So if you're all caught up with all the assignments, including the application problems that we have here for module 5, then you probably don't have to come on Friday because you don't have anything to do. Okay. But if you're not quite there, I don't want anybody to think of that as a penalty. It's never a penalty. It's an opportunity to have work time and be available to answer questions that you have. Okay. So if you're in that boat, that's totally fine too. All right. I'll expect to see you. So if you don't show up and you have any missing assignments, it's an unexcused absence. Even if you tell me you're not going to be here, you need to be here. All right. You don't get out just because it's Friday. All right. It's nice when it works out, but sometimes it might not. All right. So that's what I've got for you. Any questions? Okay. Then I am going to stop recording and I'm going to let you guys work then the rest of the time.